reactive energy balance initially. So these two can be coupled. And then we go to chemical reactions, all the heat and energy effects that take place. For example, due to the heat of the reaction, etc., and how we quantify them. And that's, I think, the two different topics that we can cover in the next few weeks. And one Sunday, we will ask for the bio portion. So that way you have all of the three, and then you go for mid-sem break. And before you do that, you have the complete thing, and then you can do your group presentation on a particular process or product or what have you, which combines all of these things. So you asked me, well, about degree of freedom. So I told you that it is related to the number of information we have, the number of nodes there are, and how many equations we can write relating these variables. And the difference between that, we said, is a measure of the degree of freedom. So I think that is a quite fairly general definition. Now, suppose we had to apply this to a non-ideal system. So that is another thing. You have already looked at ideal gases, and you know the equations that characterize those ideal gases, and you know you can how its internal energy goes, and there are many examples you have done on ideal systems, but you can't extrapolate them to non-ideal gases or non-ideal liquids or non-ideal systems. In fact, how much have you done on other than gases? Not very much. And these liquids and these mixtures of liquids and vapors, they don't behave ideally. So then we can't resort to those equations of motion. And how do we actually do the energy? There are energy changes, as you know, in phase changes, there are energy changes also. Similarly, there are sensible heat changes. So for a non-ideal system, how do we quantify these? First, non-reactive, non-ideal system. So the one improvement we want to do over all your previous high school and JEE material and first year courses is how to treat some non-ideal systems for energy balance. That is, changes in enthalpy, changes in internal energy, changes in entropy. How do we find that out? Well, it's a much more difficult question. There is no simple answer to this, but however, nonetheless, we want to do this in the next couple of weeks. So how am I going to do it? So the answer is, you need a lot more data. You need a lot more information than if the system were just an ideal gas and you had an ideal gas equation of state. For gases, it is still manageable. There are many new equations, like the van der Waals equation, that much you did. Then there are many more improvements. But what if it is not a gas? Things become quite complicated. So what I thought is, of course, like carbon dioxide, it's a very non-ideal system. Even as a gas, you can't apply your ideal gas or even van der Waals gas equation of state. You will completely go bonkers and under-predict or over-predict all the thermodynamic property changes if you were to use these equations. Similarly, what is, however, the most commonly used species in chemical industry? What is the agent that we use most frequently in all the process industries? Answer is water or steam. And steam is one great example of a non-ideal system which can exist in one or more than one phase, So you can have a combination, a phase of liquid and vapor together, for instance. You can have a sublimating system with 3 phases. So it's a very non-ideal system, and yet we want to. Yet the good thing is that all the properties of water and steam have been measured perfectly. These are there in charts and tables, and show what is with respect to a reference, which is generally 0 degrees Celsius. So if the internal energy at 0 degrees Celsius is 0, what is the internal energy at some other temperature? For steam, this is known. I don't have to give you any data. You can just go to the tables, and all the measurements that we need over whole ranges of pressure, temperature, a very high pressure system, a very high temperature system, everything, the information is available. Otherwise, suppose I replace the water with some other ammonia, a very polar gas. You don't have that information as simply. So where do I get all of that data from by which you can calculate? So that's not a great, but water and steam are a wonderful example where information is available, yet the system cannot be treated by ideal equations, ideal gas equations. So we should be able to, at least for the case of all processes involving water and steam or their mixtures, we should be able to get the energies associated with all these changes perfectly, because the data is at least available. So the question is, how do we do this? That's what we want to do. That's the first thing. Then next, we want to cover, here there is only physical changes taking place. There's only physical changes taking place, right? You're converting water to vapor, then you are removing the last droplet of dew, or if you are evaporating something, or vice versa, right? But we can also have chemical reactions. Now, when we have chemical reactions, you can have flue gases going out at different temperature from, let us say, the gas is coming in, and then they are also forming a reaction, and the reaction is associated with its own heat exchange, heat change, enthalpy change. And you have heard of enthalpies of formation, and we should be able to calculate that, and we should be, to this physical changes, we have to add all the chemical parts. So that's the other part, and that's about all that we can do in the next 3 weeks. Okay, so these 2 applications I want to take up. So when, let us say, we come to steam, nonetheless, a sample of steam can be, as I said, in one phase, say pure liquid, water, pure vapor, but it could also be a mixture, right? You can have a vapor steam coexisting with liquid steam in equilibrium. So a lot of the time, it depends, the enthalpy, you see, the thing is, enthalpies of a vapor is always much higher than enthalpy of a liquid stream, right? Similarly, ditto with internal energy and S values, H values, U values, S values. So very often we have to find out what is the state of this steam, and that is not as trivial as you think. You may have all the information, but determining what is the state of the steam, is it one phase, is it 2 phase, is not the simple. I mean, it requires some thought. So what we have now then is a general problem. Suppose I have a container, closed container. Here I have steam of 1 phase or 2 phase, as I said, but in general, let us say we can generalize it. We have any number of phases. And here we had only single component water, but suppose I could also say that there are large number of components coexisting. And now if I shake all of these things up and allow them to settle and wait for a long time till equilibrium is reached, the question is how many equations can we write and how many independent variables does such a system, multi-phase system have? This you have to think. And answer to this we have to use also in our further deliberations, particularly after minor. So the question I'm asking is, how do I determine how many degrees of freedom are there in this closed vessel containing any number of components n and any number of phases m? Do I suppose I vary a temperature? Is everything about the steam decided? Is it enthalpy fixed? Irrespective of the pressure, suppose I vary pressure and temperature both, then will it, in what condition will the enthalpy and the internal energy and the entropy and all the thermodynamic properties, how can we fix them? So what you have to really think on, how many, if I in this system contain say and the p number of phases in the container, how many variables do you think there is in this problem? And essentially, after an equilibrium is reached, after if we give it enough time, what happens? Let us say these phases can all be distinguished. Say they are all liquid phases or vapor phases, and you can actually distinguish them. Say they have different densities if they are liquid phases, so you have nice layers. The question is not the easiest question when I ask it like this, by the way, but you have to really think on this. How are the species going to distribute among these various phases? Is my question making any sense? बिकॉज टीम टेबल्स में वो टेबल्स होगा तो पर भी हमें पता लगना चाहिए ना कि कौन कौन सा टेबल ले, एक सिंगल फेज का ले, दो फेज का ले, प्योर वेपर है, लिक्विड वेपर कॉम्बिनेशन है, प्योर लिक्विड, हाउ आर वी गोइंग टू डिटरमिन दैट? That depends on the number of degrees of freedom that are there in that parcel of steam. How are we going to determine that? I said you have to determine the number of variables, number of independent equations, and subtract them. So think on this and come up with an answer. We have very few people, single digit numbers, so you should be able to, it should be more like a question and answer thing when we have just 8 students, 7 students actually. फर्स्ट ऑफ ऑल मेरा प्रश्न समझ में आया नहीं आया?
Sir, can you just explain it once again?
यार मैंने 2-3 बार एक्सप्लेन किया है, मैं कैसे एक्सप्लेन करूं? है ना, एक कंटेनर है which has all of these species mixed together. They are not necessarily only in one phase, they could be in different phases. You could have a vapor, you could have a liquid, you could have more than one liquid phase. So my question is, what will happen to each of these components over all these phases? If I had a method to analyze each phase for its composition, what will you find? Another way of asking that question. This is a general question. So as I said, इस पर आपको सोचना है. Ideally, I want this then because we have only 7 students, so we should be able to discuss this.
Sir, this is a batch process, right?
Batch process.
Yeah.
A very cruel way would be to set a question on what we are discussing now. So I mean, some IITK professors used to enjoy doing this, but okay, I mean, it's not a good idea, you know. In the next, maybe tomorrow also, it will be like this. So only 7 students, one fantastic. And completely ask nothing on the mass balance. Wow, I think there will be rebellion. Anyway, that's my question. You can ask this question in so many ways. Another way is, कितने equations लिख सकते हो आप relating every species? I am not asking you what these equations are. I am just asking you the number of equations.
So can we say that there would be the like simple state variables like pressure, volume, temperature, and the molecular concentration of one of the species, which can moles of the other species can be related by the stoichiometric coefficients of the reaction taking place.
Okay, to simplify it, let us say that we fix the pressure and temperature.
Okay, sir.
So now look only at the composition of this system. I mean, we can do that, no? We can always analyze a chemical system, and that's a very well-known method by keeping pressure and temperature constant. Since the numbers are very small, I have a really good mind to sort of ask you something on this also in the minor. We also have tomorrow, right? But that's a kind of screwy type of thing. I mean, normally I don't like doing that. Suppose there are n components and there are m phases or p phases, whatever. What will happen to these components in every phase? The answer is they will distribute. All of these components will get distributed among all of these p phases. I am not asking you find me the final distribution. That's a much harder question. I am just asking you how many such equations can you write which relate to these compositions of each component in each phase. If you want, you can look at it from the, I'm looking at it from the side of the knowns, the equation, but you can as well look at it from the side of the unknowns. How many independent variables are there in such a question, such a system? Whichever is convenient, you can start from any place. Okay, how are you going to characterize their compositions by? Now the temperature and pressure are fixed. How will you characterize composition of every species?
So by the volume they occupy in the reaction vessel?
Volume is an extensive property. We want to characterize only the intensive properties.
Okay.
वॉल्यूम से हमें क्या मतलब? वो तो हम पर यूनिट वॉल्यूम ले लो, स्पेसिफिक क्वांटिटी लोगे तो उससे कुछ, बिकॉज एंथैल्पी एनर्जी बैलेंस आई कैन डू पर यूनिट वॉल्यूम, नो? So all of those are, yes.
So sir, if pressure and temperature are fixed, then we can use the molecular mass to find out the density of the components.
Concentrations.
Yeah.
Mole fractions. That's what you will characterize them by. You can measure the concentrations of the mole fraction of every component in every phase. Why not? Why not? There are so many methods to do that. You can have an assay for, once you know what are the components, you can always assess what is the composition, what is the mole fraction of each component in each phase, right? Yes or no? Yes, of course. So I'm only asking you, how many such independent variables are there, and how many independent equations can you write which relate to these independent variables? Because there is equilibrium, no? Phases are in equilibrium because you shook them and you waited for half an hour, and then there is no change now in any of the compositions. Whatever you measure have reached a steady state. Or rather I should say have reached an equilibrium. अब उसके और कोई further change नहीं हो रहा है. Whatever you measured, if you measure now, after further time you will get the same number. That is what I mean by equilibrium, right? So equilibrium mole fraction is constant, no? If I have a mixture of ethanol and water, and I say the ethanol is 20 mole percent, and I look at its vapor phase, it will be more enriched in ethanol than water because it's more volatile, and I can say, oh, in equilibrium this has 40% ethanol, right? And that number is 40% and never lower because it has reached its maximum. So how many such variables are there in each phase? So now I am making it even simpler for you. How many such variables are there? You just have to enumerate how many they are. Why? You will have as many variables as there are components, don't you think? Why not? In every phase there is a distribution, equilibrium distribution of these components. So if every phase has component 1, 2, 3, 4, 5, ... n, each composition, mole fraction or concentration is an independent variable, right? I mean, it is a variable. Let's not call them independent. That we have to determine if they are independent or not. But each one is, you can separately do an experiment, don't you think? Yes, you can. So you will have as many variables as there are components. The question now then becomes, how many of those compositional variables in terms of concentrations, how many are independent?
So, like, how do we characterize that independence? Like, what should they be
Meaning, what
independent of?
is the way you characterize it? What is the minimum number of variables that you need to exactly specify everything about that phase? Do you need, suppose you had n components, you would have all of these in each phase. Are all of those n independent or they are not?
So, but that depends on the information, the extra information provided in the question, right?
No, it doesn't. The number of independent variables that you have in every phase is fixed and depends on the number of species that you have. At least in the aged condition where there is no further change taking place in the compositions. I'm not talking of the transient phase where things are redistributing. Once there is no redistribution of components among phases, then it is a equilibrium distribution. आप सोच नहीं रहे हो? Okay. Do you need to know all those concentrations of every component in every phase? Or if you take one phase at a time, each phase can contain each of those components, don't you think? Maybe one of them is 0, but in general it can contain all of the components. But how many of those components are independent variables? There are n components. In general, there could be all of these n in every phase. But are they all independent is my question. Or how will you find out? As I correctly, I already answered you that in general, all the n components can be there in every phase. Question now is, are those you? So you'll have n. If you could use an assay, you will get n numbers. In this vapor phase, acetone was so much, ethanol was so much, water was so much. But all I'm asking you is, are they all independent or they are not all independent?
So I have a question.
Yeah.
So are these components interacting amongst themselves?
Well, they would be interacting among themselves in the phase before they reach their final distribution. But once they reach the final distribution, there is no, you don't need to worry about the interactions. Obviously, it was some interaction which made them redistribute among the different phases. The compatibility, hydrophobicity, whatever you call them, depending on their ionic nature. But we don't need to worry about that because we've already reached the final distribution when all of those interactions took care of themselves. I am saying that the final equilibrium distribution, you don't need to worry about what you just asked. Of course, if I ask you how do they reach this or at any intermediate transient time before this distribution is reached, then it's a very hard problem. Of course, I mean, solve karna is a no joke. But what I'm asking is after all of those interactions have led to a final state. There was an initial state when you mix them. You waited a long enough time for all these interactions to happen and then you reached a final state. When everything is equilibrated and there is no further change in the composition of any phase in terms of the concentration or in terms of the composition of the components. Am I all clear on that?
Yes, sir.
Yeah. So that's my answer to your question. I think we should also set a question on this type of question in the minor, not just the mass
So,
balance we have
so
spent
I
a
guess
long.
if you can give an example question for this, then it'll be
Well, I will
it'll
give
be
you an
easier for us to
example.
understand.
Anyway, we have to take examples because I mean, when you come to steam, steam can have multiple phases. No, it can be liquid and vapor. So in liquid and vapor, let us say you also have a mixture of steam and some other solute in steam. So the vapor will have the solute. It will also have the water or the vapor of water, and liquid will also have both of them, right? So that's a two-component, two-phase system. I'm just saying, in general, it can be you can have every species in every phase. So I am just asking, utne n species. I am saying that all of the n are not independent. In every phase. So how many are independent? Answer is only n minus 1 are independent. Suppose you were to take one phase, liquid, whatever, and that has all these n components distributed. And suppose I characterize them in terms of their mole fractions. Only n minus 1 mole fractions are independent. Correct? Yes, of course, because total adds to 1. So all the n equations, all the n components variables are not independent. Only n minus 1 in each phase are independent. Like that you can write in every phase. The variables are n minus 1 independent variables and they are there in each phase. So if I have p phases, I have p times n minus 1 independent variables. Yes, of course. See, because I told you that degrees of freedom, which is a question you had only asked 2 lectures ago, I mean your class, that how do I identify them? So the way you identify them, you identify the number of independent variables and you identify the number of independent equations and subtract them. That's how you identify them. So you have now identified for an equilibrium system where everything has no change is taking place with time. The number of independent variables is the number of phases into n minus 1, where n is the number of components.
But to get a final solution, you need to have, if you have n minus one independent variables, then you need to have n minus one independent equations.
Provided the system has no degree of freedom.
Yeah. So like then if a system has a degree of freedom, then you can't basically solve the problem, right?
Correct. Exactly. That is why this is important. So if you have n minus 1, whatever, your equal number of independent variables and equal number of independent equations, and you subtract them, 0 means everything is determined about the system. Per mole or per kg or specific enthalpy is known, specific entropy is known, everything will be known. But suppose that this difference is greater than 0. Let us say I have more number of variables than I have equations. That is what I mean by degree of freedom. So if the degree of freedom is 1, what it means is that the number of variables exceeded the number of independent equations by 1. That means I have to specify one more additional parameter of state. then only I can solve it.
Yes, sir.
Suppose that difference is 2, then I need 2 independent parameters of state. Could be temperature and pressure or what have you, I don't know. If that number is 3, you would need even more information. So what I'm saying is that this difference in the number of independent variables minus the number of independent equations that you would write relating these variables is the degree of freedom. And I told you that every phase you can write n minus 1, where n is the number of components, independent equations. And since there are p phases, I can write essentially total number of equations that I can independently write is p into n minus 1. This is the total number of variables, sorry. Now find out how many equations you can write relating these independent n minus 1 variables. And then we can subtract them, and that will tell us what is the degree of freedom. 0, 1, 2, it'll be some integer. If you were to substitute for n and p or whatever. So you just wrote, you told me that there are n minus 1 independent compositions in every phase, and there is like that p phases. So p into n minus 1 is the variables that you have. Now how many equations do you have? Because if I subtract from the number of variables, the number of equations, that is the degree of freedom. So you know the number of variables that you had, p into n minus 1. Now tell me what are the number of equations.
So 3n minus 3 minus degree of freedom.
No, degree of freedom cannot come in the thing because that has to be independent. Degree of freedom has to be derived from this. So I cannot use the degree of freedom in my answer.
So with the number of
the
equations
difference between these two.
It will depend on the question, right?
Yeah, you have to identify how many informations you can write about these different phases which contain all these components which have distributed. कितने equations लिख सकते हो आप? Suppose there were only 2 phases, liquid and vapor. Let us say steam in vapor in equilibrium with water, and you are just one component. You are not thinking now. The phases are all in equilibrium because all distribution has stopped.
So basically, like what we can write is like, since the number of moles of the substance would remain constant.
Yes.
Or
so the
like
potential,
you can say anything like the mass remains constant or the number of moles remains constant.
What you can say is nothing is transferred. So in the very general sense, their chemical potentials of that component is the same in both phases.
Yeah.
And then only there will be no transfer. Otherwise, it will keep distributing. Correct?
Yes, sir.
Hey, अगर पोटेंशियल डिफरेंस होगा तो करंट तो फ्लो होगा ही होगा, लेकिन मैं पोटेंशियल को इक्वलाइज कर दूं तो क्यों करंट फ्लो होगा? Same way, if I equalize their chemical or electrochemical potentials, whatever, depending on whether the species is charged or not charged, uncharged, then there will be no further movement. And so between two phases, I should be able to write one equation. So now my question then is, if instead of two phases, there are p phases, how many equations can you write? For two phases, you wrote this one equation, equality in whatever way. No further transfer, potentials are the same. एक equation लिखी आपने उस component के लिए. Suppose there are more than two phases.
Then I guess you can write p minus 1 equation.
Let me think. Actually, equilibrium is a pairwise concept. Suppose I had phase 1, 2, 3, then phase 1 and 2 are equilibrium, 2 and 3. So basically, you are right that you can always write P minus 1 if P is the number of phases. You can write P minus 1 equilibrium, equality of potentials, or whatever equations. But now this is per component. So since you have n components, how many equations can you write? That times n, right?
Yes, sir.
N into P minus 1 you should be able to write. Because pairwise you got one equation. So you get one P minus 1 independent equations per component. Like that you can do it for n components. So n into P minus 1 is the number of independent equations that you can write. And the number of independent variables was n minus 1 into P. These are the compositional, concentration dependent. So the difference between these two is the number of compositional degrees of freedom. उसको subtract करके देखिए क्या आता है. What do you get? When you subtract this number of independent variables and independent equations, what do you get now? You just told me n into P cancels. So you will get n minus P, correct? And now if you add temperature and pressure, you will get your Gibbs's rule, which is that the number of degrees of freedom is equal to n minus P plus temperature, pressure, so 2, so plus 2. That is exactly how Gibbs would have derived this rule. That is the number of degrees of freedom. So that is why Gibbs said that for a system in equilibrium, general system, if there are n components and P phases, then n minus P plus 2 is the number of total degrees of freedom. That is a very important result for us. So if that n minus P plus 2 gives me a positive number, utna hame extra information dena hoga in terms of parameters. So suppose that number is 1, that means suppose I specify temperature, then everything about that parcel of steam is determined. All its how many per unit mass, everything is determined. How much internal energy it contains per kg, how much enthalpy, how much entropy, everything is determined. Suppose that number is 2, then I have to specify 2 quantities to determine all the specific heat or specific energy components and specific energy parameters. I won't say call parameters, specific energy of that parcel of real to steam. That would be a good place to end it, and we can try actual application. You can actually get wonderful, very complex systems which are non-ideal. You can actually do them exactly to the decimal point, as depending on how good the data of enthalpy, entropy, internal energy, volume, pressure, density, etc. is available for steam, which it is. So you can solve very. You can heat something, you can cool something, you can do something isentropically, you can do some expansion, you can do an isobaric process, and all for a non-ideal system. अभी तक तो आप ideal gas के लिए करते थे ये सब ना, correct? Did you get it, देवप्रिया, भव्य, आशी? ये तो आप आप ड्रॉ करते थे ना डायग्राम, कार्नो और ये पीवी डायग्राम, बट वो सब आइडियल सिस्टम के लिए करते थे आप, RTLN, this by this, etc. But now we can do it for steam or any other non-ideal system for which enthalpy, entropy, volume, specific volume, internal energy data is available. That's really what we want to reach. Okay. So,
Okay, sir.
So is there any maximum number where the degree of freedom
that depends on the difference
can go to, like
the number of independent equations and the number of variables.
no sir, like is there any like
No.
no asymptotic value or anything
No.
Like it
because
can go to any number?
Because n minus p doesn't have an asymptote.
No sir, not asymptote, like a maximum value or a maxima where it can reach.
In theoretically, no, but in practice, yes, because the complexity of the system is limited. We have only, if I take steam, I will have only one component, no?
Yes, sir.
So it will limit the number.
So, but like if you see like the number of phases possible are like,
yeah,
like generally it's only 3 or maximum it can go to like 4 or 5.
Exactly. So that will limit it. The number of states of matter will limit it. But in principle, mathematically speaking, there is no such limit. But since the number of distinct phases, regions of matter is limited, and the number of components that we deal with is not infinite, but generally in first we'll do with steam, which is just a single component, water, just a single component. Then if we won't reach there, but we could have impurities in that, we could have some electrolyte in it. But those are more complicated things. Or we can add NaOH, for instance, we can have sodium hydroxide solution. That will have a different answer, no? I mean, then you have a 2-component system, becomes harder and harder. But right now we will only look at steam. वो सब तुम acid, base, and impurities, electrolytes, वो तो beyond the scope of this course, right? We have to calculate exactly all the energy balance for steam doing any type of process. That's what I would like to teach you.
So like we are going to calculate the parameters related to, say, we are heating steam in a batch process, heating water in a batch process, and that is producing steam.
Right, not just heating, Devpriya, anything. You could have a isentropic expansion with steam. You can have an isenthalpic some process, or you can have an isobaric whatever you want, you know. You can have a process where the temperature, pressure is changing, and you understand. You can do anything you want. Go from state 1 to state 2. You should be able to calculate all the energy differences in internal energy per unit mass. If you know the mass, you know the total internal energy difference, the total enthalpy difference, entropy difference, everything. And this is a non-ideal system. You can't apply your PV equal to business, no equation of state that you know. All right?
All right, sir.
So like the degree of freedom was basically the number of physical parameters that we need to specify, right?
Exactly.
So
the number of physical parameters you have to specify to completely determine the state of that component, in this case steam, per unit mass.
Won't the number of physical parameters be like limited?
Yes, they will be limited in practice, yes. But the equations
not only in practice, like even theoretically, if you say like aren't the number of physical parameters like limited for any reaction, like?
Well, now we are getting into semantics, you know. I mean, let us let us postpone this discussion of this. But my point is, for steam, you are absolutely right. You are correctly understood that what this degree of freedom is telling you is the number of physical parameters you specify to exactly specify all the energetic and parameters per unit mole or mass of that steam, of that component. Specific enthalpy, specific or molar enthalpy, or specific internal energy. Everything has to be, we have to calculate for any type of process, right? That is what we need to do in the next couple of weeks.
So that's why, like, I was asking, does it reach any specific boundary condition? Because like there are only so many physical parameters that can be specified, like temperature, pressure, or potential, etc.
Yeah, generally, you know, it will be temperature, pressure, specific volume. But you know, many times the independent variables can be anything. suppose I give you a specific volume initially, and I give you a final specific volume, and I give you some process linking them, and I ask you what is the final temperature. You should be able to do all. There's so many permutations of this problem. Okay. Anyway, we continue. We can't do this in one class. Okay. This is going to take us about 4 5 classes. Okay.
Okay, thank you, sir.
Right. Good luck. Yeah. And I mean, maybe I should set something on this. I have a good mind.
Well,
An example in the next class, and if like probably we can get an idea with that example.
This exam, this was supposed to be after minor, but now I have to think. I mean, since there's so few people, maybe we should set something on this also. I'll see. I generally don't do this type of thing, but I have a good mind this time too. We should always be unpredictable a bit, otherwise people take you for granted. So maybe I'll set
excuse
something.
me, sir.
Yeah.
Sir, tomorrow when you just give us a problem on this, a particular
We have
type,
not
could you
reached that.
also give us a few?
Yeah,
So,
actually, we have
sir,
not reached
will
that.
we have it?
But
Okay,
you
sir.
can ask so many questions which may not be linked to a particular problem. For instance, how many degrees of how if I have n phases and if n components and p phases, how many degrees of freedom are there? You just calculated it for me. You said it's n minus p, right?
Yes, sir.
I mean, I can ask so
Yes,
many.
sir.
I can think of so many questions which don't relate to an actual problem because we haven't reached. We aren't in that happy state where we can actually calculate. It's a calculation course, no doubt, but ये तो आगे का है ना, ये एनर्जी बैलेंस शुरू कर रहे हैं, है ना?
Right,
तो
sir.
तो पहली क्लास में हम कहाँ से कैलकुलेट कर लेंगे एक या दो उसमें इसके लिए हमें जस्ट एज मास बैलेंस also we were able to calculate many things. Now energy balance also we will calculate, and what I want to do, I'm not happy with just ideal system. Ideal system तो आप करके मैं बोर हो गया हूँ. So we want to do for a non-ideal system. I just took steam because उसके लिए सारे properties of as a function of temperature, pressure, everything is there in the handbooks. The internal energy, enthalpy, etc. Entropy for per mole of steam or per kg or per gram of steam, right? And its densities, specific volume, everything So वो data ढूंढना नहीं तो data कहाँ से लाओगे? Without data you can't solve this, right? Okay, good luck. Yeah, we'll continue tomorrow.
Thank you, sir.
Thanks, sir.
Right.
Thank you, sir.